Welcome to a presentation on AtomProbeLab, a collection of MATLAB scripts and functions for the analysis of AtomProbe data. So this gives you a kind of overview of the different functions that AtomProbeLab enables. It's a bit of a hodgepodge of lots of different things, and that's because of the history of the development of the library. So it started out with work in my PhD, and then it's been developed and updated and made open source. And it's available for anyone to download and use if you've got MATLAB. It mostly revolves around solving peak overlaps and doing composition quantification, but there are some other tools in there as well. I'm just going to focus on a couple of these in this quick talk. Again, mostly just highlighting some key features, but do go and have a look at what's available. First of all, I want to talk about overlap diagrams. This is a concept that I've introduced, and it's a way to easily summarize the overlaps that you have in your mass spectrum. On the left-hand side, you can see a simulated mass spectrum. Here we can see the different peaks colored by the different species, and above we've got the labels for the different peaks. So the lines show the theoretical peak positions. The widths of these bars actually show where and how abundant each of these different isotopes are. So you can see here for titanium, this is the most abundant peak, and these ones are less abundant. And this nicely shows where the different ions are and how they spatially overlap in your mass spectrum. On the right-hand side, there's a graph showing how these different species overlap. So here, for example, we can see that zirconium 2+ overlaps at the 45 mass position with this iron oxide species. And we can actually see that directly here. So here is the small isotope of this molecule, and you see it overlaps with zirconium. And this gives a very easy visual way of summarizing where different overlaps are happening and what ion species are involved. And even the thickness of these lines, which indicates which species overlap with each other, the thickness indicates how strong that overlap is. So in this case, between iron O2 and zirconium, there's not a very strong overlap. This is a very small isotope. So this is what we consider an easy overlap to solve. And between something like zirconium and zirconium hydride, you see they share a lot of different peaks. And this makes the maths of solving the overlap problem actually more difficult. And so that gets colored with a slightly thicker line. So the other thing that's quite important are confidence intervals. So the way these are calculated in AtomProbeLab is that a Monte Carlo simulation is performed assuming a Poisson distribution of counts for each peak, where the average of that distribution is the measured counts in each peak that you've observed. This is solved by maximum likelihood estimation in order to give a set of measured peak overlap solved compositions. And that set of compositions gives you a distribution, and the start and end of that distribution, or the 5% and 95% range of that distribution, gives you your confidence interval. So this directly tells you how difficult your overlap problem is to solve and what the confidence in your answer will be. Now there's a couple of demo scripts that show this overlap solving. One of them does it when you have a bulk dataset where you just want one answer for the whole dataset. This gives you the lower and upper confidence intervals as well as your estimate for your composition. And there's another one which does overlap solved line profiles where you get the composition and an error bar for each of the different positions along your line profile for however many bins that you've chosen. The confidence interval estimation takes into account the effect of the local background subtraction, and you can also output the results as weight or atomic percent if you want. Something which is really important and I've been working on fairly recently is figuring out which ions should be chosen for a particular data set. If you look at the data here, if you're familiar with working on steel, you might recognize this mass spectrum as containing iron and maybe nickel. But there's a question, do we include aluminium here? Should we include silicon or carbon monoxide in this 28 peak? And actually there is a rigorous statistical way of doing that. And that's what's included in the ion fit tester function. And there's a demo of that. And this is a little snippet of the output. So it uses this information theory, the AIC value, where lower numbers are better, and we've also got a probability here as well. So 100% is the best, and then as you get smaller numbers, that's worse. And this shows you the different ions that it's fitted and their relative proportions. So the most abundant ion followed by the less abundant ions. And we also have the effect size included here. So the effect size tells you how well your data fits, and it's kind of like a normalized residual. So a large number here is bad. That means poor fitting. So even if you only had these bottom only these bottom fits here, you could tell, even if they apparently had good AIC values, in this case they don't, but if they did, you could tell the fit was wrong just by looking at this effect size. So that the information criterion tells you which of your different models that you've got, which one is best, but it doesn't tell you if any of them are outright bad. Using the effect size gives you an actual quantification of how good the fit is, and you can look at the other goodness of fit objects, and you can choose your own metric for deciding how good the fit is. And you can see there's actually a couple of different choices here. The actual data is iron, nickel, and it should be silicon, but there's a very, very small amount of silicon here. And what that shows is that depending on how hard your overlaps are to solve, it might not be possible to actually use this method to robustly pick out which is the correct true value. So there is a sort of sensitivity of this method. So it's not a cure-all, but it is a reasoned quantitative way of deciding which ions you should be including in your data. And just out here is an output showing the fitted values, which is the coloured bars, to the observed data. So that's observed from this mass spectrum here, the little crosses. So you can see this fits, even just fitting with iron and nickel fits very well. And there is just a small amount of silicon which is hidden in there, which we can't see. So do please check out the website and contact me by the email address there if you have any questions. If you'd like to download the software, you can go to SourceForge and follow the link there to AtomProbeLab. Hopefully that's in the video description. And this is the page that will greet you. You can see a short description of the project. There are some screenshots. You can check out some of the papers that I've published on this topic. If you go to the files section, then you can download the latest version and look at the README. But if you want the latest up-to-date version, hit the Mercurial tab here. That's the version control which is used, and you can hit download snapshot. And what that will do is it will get the latest branch of the code which has been developed, and you'll get all of the any bug fixes that are included. You can use the other versions in the files list, but I would always recommend using the snapshot button there. If you download and unzip that file, you'll end up with something that looks like this. This is what libatomprobe looks like when you open it. There's a bunch of demo scripts here. These give you some idea of how to use different functions. There are some data sets included here. If you look in the source file, you can see these are all of the different functions. MATLAB has each of its individual functions as separate files. That's why it looks like there are so many files here. Each of these has its own dedicated help at the start of each of the files, so that's how you can get help in the sort of the function help. If we just click on one of these to demonstrate how they work, we can have a look here at MATLAB. This is one of the scripts. If I just hit F5 to run this, it's going to ask me to change the directory, which is fine. I'm just going to change the folder now. And you see on the left, we've switched to the AtomProbe directory. So this is the AtomProbeLab directory. This is wherever you put it. This is the output of this particular demo script. It shows you the overlap diagram for this problem, which is very straightforward. It's plotting the fitted counts and the decomposed counts. In the terminal at the bottom here, we've got the composition output. And we've got some other output from the terminal, so a warning here about the O2 isotope, which wasn't included. If we look at any one of these functions here in the script, so if we look at the overlap problem builder, I press F1 with that function highlighted, we get the help text. So this tells you how you can use the function, what the various different inputs are, examples, outputs, any notes that you need to make note of. So you should have help for this for all of the different files that you need to use, and the demo script should show you how to use these different functions as well. As a final thing, there is a wiki on SourceForge which you can check out, and this has some detailed explanations for certain scripts, but this is a work in progress, and I hope before I'm kind of finished with AtomProbeLab and start moving things over to libatomprobe that the wiki will be minimally complete. And with that, thank you for listening.